Alrighty. Okay, let's go ahead and get started. So for all these, remember that the area formula for a triangle, 1/2 times the base times the height, right? So if we want to find the area of a triangle here, well, this first one has a base of 2 and a height of 7, right? 1/2 times 2 times 7. Half of 2 is 1, times 7 is 7. So for number 1, the answer is 7, right? Same thing for number 2. 1/2 times base times height. Now, it really doesn't matter the order in which you multiply these, right? So if you want to do 1/2 of 12 and say, hey, that's 6. 6 times 5 is 30. Or if you want to do 5 times 12, that's 60. 1/2 of that's 30. You want to do 1/2 of 5 is 2.5. 2.5 times 12, still 30, right? Doesn't matter which way you go. All that matters is that you get the same answer right. All right, last one. The base is 3, the height is 5. Well, again, this is one of those situations maybe you want to do it the easy way. 3 times 5 is 15. 3 times 5 is 15, and then 1/2 of that is 7.5, right? So what are we doing? We're going to be able to find the area of a regular figure. How are we going to do this? We're going to need to find the length of the apothem and then the length of one side. We'll see why in a second. Also, what's an apothem? I don't even know. We're going to find out. Why? Well, the thing of it is, we've talked about all the simple figures that there are. Now we've got to start branching out and doing other types of things here. All right? So basically, this is sort of the last type of shape that has an actual like standard process for finding any type of regular figure. You're always going to be able to do it basically the same way. The numbers are always going to be a little bit different, but the concept always going to be the same general process. All right? So let's start out with a little bit of background. So here what I've got is a regular pentagon and the radius. So when we're talking about the radius, how do we deal with that for something that's not a circle? So a radius we define as going from the center to the corner. All right? That's what we mean by radius when it's not a circle. Apothem is from the center to the middle of a side. It's like the other extreme. This is the farthest distance from the center to the outside, and this is the shortest distance from the center to the outside. As you have more and more sides, you know, that's a pentagon. If you have an octagon or a icosagon, 20 sides. Centagon, 100 sides. The more sides you have, the closer the length of the radius and the apothem get, until eventually you get to infinity sides, a circle, right? And then the radius and the apothem are the same thing, and we just call it the radius. All right? But for here, the apothem is going to end up being the important one for us, because if you notice, you see the shape that this pentagon has been cut into is a triangle, right? So we know how to find the area of a triangle. If we can find the area of the one triangle, and we just go, hey, all these are the same. So 1, 2, 3, 4, 5, right? And then we have the area of this whole thing. Now the book sort of goes about it in a slightly different way. It's the same general thing, but we're going to sort of talk about it in a little bit. All right. So what they want us to do right now is find some of these angles in here. So the first angle is this one. We want to figure out angle number 1. And what we want to think about, we just talked about this in terms of a circle, right? Radius, apothem, all that, right? Well, same idea. If we know what's a full revolution around in terms of an angle measure? 360, right? So since it's 360, if I were to go all the way around, it's 360, but I just want one of these slices, right? So for angle 1, that didn't work too well. For angle number 1, the whole thing is 360. One piece of it, well, there's 5 of them. They're all the same. So we're just 1/5 of it, right? What is 360 divided by 5? Anybody can tell me? 72. One really great way to, when you want to divide by 5, remember you can just divide by 10, just drop the decimal place, and then times 2. So drop that decimal place, 36 times 2, 72. So each of these central angles here in the middle are 72 degrees. So now what about angle 2 here and angle 3 here? So angle 2, it can maybe be a little bit hard to see here now that I have all this stuff in the way. What we're talking about with angle 2 here, we're talking about the angle up at the vertex, right? The half one. So if the whole thing was 72, right? This whole thing was 72. We just want what's half of that, right? So here, what's half of 72? 36, right? All right, now, last thing we want to talk about here is angle number 3. How do we figure out angle number 3? It's that other angle, right? So, look, we got 72 up here. Each of these radii are the same, so this is an isosceles triangle, right? Well, since it's an isosceles triangle, we know that these two angles down here are the same, right? We can call those x. Well, the 3 angles of a triangle add up to 180, right? So 2x and 72 better make 180. We can just solve, right? So all we have to do is solve for x. So what do we got? We got 2x plus 72 equals 180. Let's subtract 72 from both sides. 180 minus 72 is 108, right? And we divide both sides by 2. Half of 108 is 54. So as we're looking at this, the key to doing all these problems starts with finding angle number 1 first, the big vertex angle. We find out how many sides there are. We just count here. Pentagon, 1, 2, 3, 4, 5 sides, right? We know that the whole thing should be 360. The whole thing should be 360. I don't know if y'all can see I'm making a circle shape with my hand. But the whole thing is 360. If there's 5 of them, just divide by 5. If it was a 12-sided figure, divide by 12. A 50-sided figure, divide by 50. It doesn't matter how many sides there are, divide by that number, and that'll get you angle number 1. Now, if you want to find angle number 1, you do that, then that second angle is just half of the first one, right? So just whatever you found for angle number 1, divide it, and then angle number 2, right? And then the angle number 3 that they have here, just do 2x plus whatever angle number 1 was, solve for x, and then you've got it. All right? Pretty simple. Now, they've here been labeled specifically angle 1, angle 2, and angle 3 in that way. It doesn't matter what they label them, right? First, find the vertex angle, and then you can easily find half of that, and then find one of the base angles, right? That's what they've been asking for. All right, so here they've given you sort of a similar type of figure. It's an octagon. And they've luckily labeled them the same way that I labeled them before. Angle 1, angle 2, and angle 3 labeled in the same way. Go ahead, give this a try on your own. Make sure you can do this. All right, let's go over this. So one of the things, there's going to be, I'd say there's probably 2 ways to go about doing it. And I saw 2 different ways as I was walking around too, which is great. Some of you are going to say, all right, well, this is half of an octagon. So this piece is 180, and there's 4 sides right here. So 180 divided by 4, 45, right? Or this is the way I would do it, just because I'm one of those people that like to do the exact same thing every time, no matter what, always and forever, amen? Is I'm going to say, oh, I've got my whole thing is an octagon. Octo means 8 sides. Octo, like an octopus. So I'm going to say, all right, for angle number 1, it's always 360 divided by how many sides? In this case, there's 8. But regardless of how you do it, no matter what you do, you'd better get 45 degrees, right? Angle number 2, that's going to be half that. Well, what's half of 45? Well, it's half of 44s, 22, and then 0.5, right? And then lastly, we just want to figure out the other 2 angles. So once again, 2x plus whatever this thing is. Right, and so now since we're working on this triangle here, the 3 angles add up to 180. So subtract the 45. Divide both sides by 2. Half of 135. Well, what's half of 120 is 60. Half of 15 is 7.5. So one of those angles is 67.5. All right. Notice how it was the exact same process, right? Exact same thing we just did. Just now there's 8 sides instead of 5, right? If you keep doing the same thing every time, you get used to what you're doing, and it's just sort of you blaze a trail for yourself, right? Next one. All right, so here's where me and the book have a difference of opinion. They give you this formula and they don't tell you where it comes from. That the area of a regular polygon is 1/2 times the length of the apothem times the perimeter of the figure. Okay? That is fine. If you get those things and you just want to do that right away, you can do that. That's totally cool. But by now, y'all know I'm not about just memorizing things. I don't like to just, oh, well, here it is. Good luck, right? It's important for me because I don't work that way. I can't, I have a really bad time memorizing. My brain doesn't work. So holding stuff inside of it, that ain't go. So I need to know why things are what they are. Where does this whole thing come from? Well, think about it. The perimeter is just the length of one side times the number of sides, right? So if I were to take this hexagon and split it up, the important thing is that I tried. If I take a hexagon and I just split it up, and then I unroll it into those triangles like we had before, think about it, right? I'm absolutely 100% going to need to recalibrate this because it is way off. But look, here's the thing. The apothem is just the height of a triangle, right? The perimeter is just the base of a triangle, and then how many triangles? It is 50 billion times easier for me, instead of thinking about it like this, think about it like one half base times height for a triangle times how many triangles there are. To me, that makes a lot more sense. It's a lot easier to like understand what's going on. All right. But now, of course, like if you're given the perimeter and the apothem, and you just want 1/2 times a times, that's fine. Yeah, do that. But if you're sitting there and you're saying to yourself, well, they don't give me the perimeter, they don't give me the apothem, what do? If you can go back and use your triangle knowledge, and you can figure out what's going on with your triangles, suddenly the problem becomes a whole heck of a lot easier to do. All right? So my recommendation generally is to reconsider what you're actually looking at. Instead of thinking about it as this 10-sided regular polygon, think about it like something that got cut up into 10 pizza slices, and then just find the area of one slice and then multiply by 10. You know what I mean? To me, in my opinion, the way my brain works, that always feels like 50 times easier. Now, of course, I'm giving you this formula, 1/2 times the apothem times the perimeter. If that's something you want to memorize, if there's a phone number somewhere that you don't need to have memorized in your head anymore, you want to kick that out and put something else in your brain, fine. That's totally cool. All right? Speaking of, notice they don't give you the perimeter here, right? I could go through and I could figure out the perimeter. I could be like, okay, well, how many sides are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the perimeter is 80. Right? And then I can just do the apothem is 12.3. The perimeter is 80. And then I can do whatever that is, right? So 40 times 12.3. Don't do that. Do it the other way. Make sure that the one with the more digits is on top. And why is that 40? Half of 80, right? I'm just making my life simpler. So we got a 0 for the ones place, so we don't only have to worry about the 4, right? 4 times 3 is 12. 4 times 2 is 8 plus 1 is 9. 4 times 1 is 4. We've got 1 decimal place. So my final answer is 492 inches squared because we're working with area. That's totally one way you can do it, right? That's using what the book tells us. But just as easily, we could do it the other way. All right? Instead, we could be like, all right, well, I've got this triangle right here, right? 1/2 base times height. Well, what's half of 8? 4. So what is 12.3 times 4? That's the area of one triangle. Okay, and then how many are there? There's There's 10 triangles, so just times 10. I'm not telling you one way is better than the other, but I am telling you what I'm showing you here right now, especially as we go forward, as things tend to do, they end up getting more complicated eventually, and we get to the point where it's like, we're going to be given information that's going to be less helpful. And we're going to have to do more gymnastics to do a problem. And I'm telling you in advance, yes, the book has given you that formula. It is significantly less than useful, like 95% of the time. All right, just saying. All right, your turn. Regular pentagon with an 8-centimeter apothem and 11.6 centimeter length sides. All right, let's go over this.
See if you're right.
All right, so how many sides does a pentagon have? 5, right?
Mm-hmm, you're right.
Think of the building, right? The Pentagon, and it's also the shape of a, in baseball, home base. That's Pentagon, right? So rather than, because again, my brain has trouble, I'd rather just figure out one of the triangles and then times 5. So we know that the base of the triangle is going to be one of those sides, and the height's the apothem. So 1/2 base times height. And you get whatever 4 times 11.6 is. All right, 46.4 rather. That's one triangle. Well, how many triangles are there? There's 5 of them. So what's 46.4 times 5? And what are these in centimeters? Squared. 232 centimeters squared. All right. So once again, I'm not telling you that this is the only way you have to do it. Just as easily, you could have done 11.6 times 5 to give you the perimeter, and then multiply that by 8 and divide by 2, right? But I'm going to be very honest with you. Small numbers are always easier to work with. Small numbers. Small numbers. All right? So once again, remember what I was saying is that they're not always going to give you the most helpful information. I'm giving you a little extra bit of diagram, but when you've got they're just going to give you the side here, you've got to figure out the apothem yourself. Now we're lucky this is a hexagon, right? Because if I go through, well, just like we did in the very beginning, we can find the angles. 360 divided by 6. That gives us a length of 60 here. This angle is 30. Well, so we've got a 30, 60, 90 triangle. Remember, if we want to find a 30, 60, 90 triangle's other pieces, from the small one to the medium one, we just multiply by radical 3. So if they tell you that the side of a hexagon is something, you can just cut it in half and then multiply by radical 3 to get the apothem. All right, does everybody hear what I just said? This is the long and short of it. If you've got a hexagon and they give you the length of one side, cut that side in half, multiply by radical 3, that gets you the height of that triangle. Everybody see what I'm saying? So now, for this triangle, we've got the base is 3, because that's what they told us about the side of one cell, right? And then we know the height. Divide by 2, multiply by radical 3. I'm just going to leave it as 3 radical 3 over 2. Because they don't tell you to round, so we ain't going to round, right? We're just going to leave it. So look. 1/2 times base times height. To find one triangle. All right, that gives us 9 radical 3 over 4. That's our area for one triangle. And we're going to say, how many triangles are there? There's 6, right? For a hexagon. 6 triangles. We've got 9 times 6 is 54. And then you can say to yourself, oh, well, I can simplify that fraction, right? The 54 and the 4 both have a factor of 2 that we can cancel out, right? Half of 54 is 27. Half of 4 is 2. And so in simplest form, that is our answer. Now, if they tell us to round, are we gonna do all that hot mess? No, we're gonna throw it into a calculator and be done with it, ain't it? But if they don't tell us to round, that's the answer I want to see. Okay? That's the answer they're going to want to see too. Here, from here to here? Yeah, so I multiply all the numerators. The things on the outside of the radical multiply. 3 times 3 is 9. Then that radical 3 stays by itself. You ignore that. All right? And then same thing on the bottom. The 2 and the 2 multiply. Right? Remember, you don't want to multiply. You want to basically, when you're multiplying everything out, sort of take the radical, put it off to the side, then multiply all the numbers, then glue the radical back on. Your turn. Still a regular hexagon. I just ain't giving you a picture this time. So, remember what I said. What you want to do, if they give you the length of one side, you need to find the height of the triangle. They give you that this is 16, but we need to find this guy. So remember, since we have that 30, 60, 90 triangle going on, cut the side in half and put a radical 3 on it. This is going to be 8 radical 3. Well, now we've got our area, right? Just 1/2 base times height. The area of one triangle. Half of 16 is 8. 8 times 8 is 64. So for one triangle, we get 64 radical 3. And then there's a hexagon, so there's how many of them? 6, right? Yeah. So just take this, multiply it by 6. Whatever 64 times 6 is, 4 times 6 is 24. 6 times 6 is 36, plus 2 is 38. So this is the answer if they didn't tell you to round, but they said to round. So remember what I said, if you're going through and you're doing a problem like this and they tell you to round, you don't have to mess with all the radicals. You can just throw it into the calculator and be done with it, right? There's 6 triangles, so 6 times, half times 16 times 8 times radical 3. In the calculator, just hit the enter button and it does all the work for you. You get 665.1075.101. And then you say to yourself, all right, I want it to the nearest square foot, nearest whole number. So I'm looking at, is that 5 or bigger? And the answer is no, right? So the answer just is 665 square feet for my rounded final answer.